All right, so here, let's start looking at the Taylor series or Maclaurin series for similar looking functions. And what I mean by this is we're going to basically do this idea of stencils just like we did with power series in our friend 1 over 1 minus x. In fact, right now, let's just write out all the power series, Taylor series, Maclaurin series that we have at our disposal right now. So we have 1 over 1 minus x. That was the first power series that we figured out the function identity for. And that was equal to the series from n equals 0 to infinity of just x raised to the power of n. Next, we found out the power series or Maclaurin series form for e to the x, which was the infinite sum from n equals 0 to infinity of x to the n all over n factorial. And then we found out the Maclaurin series for sines and cosine, where sine took all of the odd terms and cosine took all of the even terms. Basically, we had negative 1 to the power of n, and then x raised to the 2n plus 1 all over a 2n plus 1 factorial. So again, just to emphasize, remember sine is odd and cosine is even. So x to the 2n all over 2n factorial. And the last Maclaurin series we found was for the binomial series, the 1 plus x raised to some power that we said was equal to p. And now this compact series notation wasn't the prettiest, but again, we figured out this pattern just by doing that table method as well, where the nth term of that series had the coefficient of p times p minus 1 times p minus 2 all the way to p minus the n minus first term. And that was all over n factorial times x to the n. And well, at this stage, we're going to do the same exact stencil game. If you don't exactly remember what that was, let's quickly remind ourselves. This whole idea with stencils was basically replacing x with open parentheses. And that was in both the function as well as the series. So if we have 1 over 1 minus x, we could replace that x with open parentheses in the function and as well in the series too. So whatever is inside those blue parentheses in our function, we can rewrite that in the blue parentheses in our series. So if we have e to some power, well, get rid of that x and write that as e to open parentheses. And we can do the same exact thing inside of our series as well. And we could do this for sine, cosine, and the binomial series, but let's actually just jump into some examples of this. So the first example, let's consider the function e to the minus x squared. Well, recall that e to the open parentheses, or let's just actually start with e to the x, that was equal to our Maclaurin series of x to the power of n all over n factorial. So if we go ahead and stencilify this, this is just e to some power equals the series from n equals 0 to infinity of whatever's in those blue parentheses being raised to the nth power all over n factorial. And well, you guessed it, next. Inside of those blue parentheses here, all we need to write is a minus x squared. And we could write that minus x squared in those blue parentheses on the right-hand side in that series as well. And we just found the power series for the e to the minus x squared function. And we could do a little bit of algebra on this just for fun. So I'll make a note. This is basically to practice algebra, but will come in handy if we start doing some other things with Taylor series, like integrating or differentiating them. And well, inside of this series, we have a product of -1 and x squared, all raised to the nth power. So we could actually separate that and write it as a -1 to the nth power times an x squared to the nth power as well. And the last thing we could do is, well, if we have that x squared raised to the nth power, that is really just an x to the 2n power. And if this should be, and we could call this our final answer. You might also note that, well, the Taylor series for this function looks very strikingly similar to cosine, except it has a different factorial in the denominator. Let's do another example of this. Say we now have the function of x squared times sine of x cubed. We're going to do the same exact idea with stencils here, except the new thing here, we're just multiplying some other term onto this function. That is completely fine. So let's remind ourselves what sine of x is equal to. Sine of x is equal to the Taylor series or Maclaurin series or power series from n equals 0 to infinity of -1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. So let's replace all those x's with open parentheses. Oop, messed up my color scheme. So now with the stencil for sine, well, we have a sine of x cubed. So let's just take that x cubed and throw it inside of our stencil. And voila, we have a power series for sine of x cubed. But that's not all, since we are multiplying that by x squared on both sides. So let's just go ahead and do that next. So we have x squared times sine of x cubed. So we'll just multiply that x squared out in front of that series. And let's do a little bit of algebra on this series. We have an x cubed raised to the 2n plus 1. And since we're raising a power of x to another power, we get to multiply the powers together. So this is really an x to the 3 times 2n plus 1 all over 2n plus 1 factorial. And let's continue doing a little bit of algebra. Next, we're going to bring that x squared inside of our series. So we have that -1 to the n. We'll have that x squared, which I'll still highlight in red. We now have an x to the 6n plus 3 power, all over a 2n plus 1 factorial. And finally, since we have the product of x squared and x to the 6n plus 3, those have the same base, so we can add their powers together. So the last algebraic manipulation we could do, we have -1 to the power of n times an x to the 6n plus 5, all over 2n plus 1 factorial. And that is a Taylor series for the function x squared times sine of x cubed. So I hope you can see how we pick up on patterns and do this idea stenciling for some of these other functions as well that already have a known power series along with them. Let's dive into some applications just using the stenciling idea and using Taylor series, Maclaurin series, or power series in general. Check it out.